Hi, my name is Brian Caffo, and this is Mathematical Biostatistics Bootcamp, Lecture 3, where we're going to talk about two-sample tests. Okay, so today we're going to first talk about match data, then we're going to talk, and match data brings up a kind of an interesting immediate discussion on the topic of regression to the mean, which has a very famous history, and then we're going to talk about two independent groups. So when you're comparing two groups, one of the first things you want to ascertain is whether or not the data are paired or not. And so it's a little less clear than you might think at first. So the most obvious instance where the data are paired is when the observations are both on the same subject. So take as an example a trial where you have a treatment, say some medication. In one case, imagine if you randomize that treatment to one group of people and randomize, say, a placebo to another group of people, then that's clearly not paired. You have one group of people that received the treatment, another group that received the other treatment, the placebo. Instance where it's obviously paired would be, imagine if you, in some random order for every person, gave them the treatment and then had maybe a washout period, and then gave them the placebo, or for some people you gave them the placebo first and then had a washout period and then gave them the treatment. In that case, it's obviously paired because you had the same person receiving both the treatment and control. So in both those cases, the question would be to compare the treatment versus the placebo, but in one case you'd have two independent groups of separate people, and in the other case you would have each person receiving both. So in the latter case, they would be paired. And in some cases, pairing is maybe a little less obvious. So for example, what might happen is you're not looking at something that's assigned. Let's say you want to compare, let's say, people with high blood pressure to people with low blood pressure, and you wanted to compare some other characteristic. Let's say we used sleep as an example the other day. So imagine if you wanted to compare the low blood pressure people to high blood pressure people and compare their RDI, their respiratory disturbance index. Well, that seems like it would be unpaired because you would have the low blood pressure people would be one group of people and the high blood pressure people would be another group of people. But they could be paired because often what people do in these kinds of experiments is they get, say, their low blood pressure people, and then for every person in that group, they then try and match in terms of age and gender and other characteristics, try to closely match for every person another person in the high blood pressure group. In that case, it would be sort of softly paired in that it wouldn't be the exact same person, of course, because a person at one given instance can't have low blood pressure and high blood pressure at the same time. But what you could have is where a person one from the low blood pressure group is very closely matched in terms of age and other characteristics and weight or whatever to a high blood pressure person. And then they are paired, they're just paired in a different way. So that's called matching, when you try to take for every person in one group, find another person in another group that has very similar characteristics for all these other variables that you're maybe not interested in, but you think could contaminate the comparison. That process is called matching, and it's a very effective way to deal with as I mentioned, variables that you think might confound the relationship that you want to look at. So in any case, the discussion for this slide for today is to simply, to distinguish between two different types of two-group comparisons, the two main types of two-group comparisons. One in instances where observations are paired, either by matching or something else. Okay, so let's consider the instance where the observations are paired. And this is the easy case, because then everything reduces down basically to a one-sample problem. So when the observations are paired, one strategy is to take the difference between the paired observations and do a one-sample t-test of the null hypothesis that the population mean difference is 0 versus the alternative that the population mean difference is non-zero or one of the other two alternatives. And then that would be a very straightforward thing to do. Your test statistic would just be the ordinary one sample test statistic, the average of the distances, minus the hypothesized mean, typically 0, divided by the standard deviation of the differences, divided by the square root of the number of pairs of observations. So you want to make sure that you're putting the number of pairs of observations in there, not the number of total number of observations, because when you start out you wind up with 2n observations, one for the first measurement and the other for the second measurement. So when you subtract them, you wind up with half the number of observations that you typically started with. So at any rate, the principal way to do this is to simply take the differences, throw out the data, and treat the differences as if they were a one sample test, and that's the ordinary paired two-group t-test. Okay, so here's a simple example of doing a paired t-test. So I took data from 2 exams from a particular class one year. So I had 2 exams, so clearly the data are paired because it's the same students measured twice. And so let's make up a question. So I have exam 1 and exam 2, and in the question I'm going to try and ask, is there any evidence that the second exam was easier or harder than the first? And that one way to investigate that question would be to ask whether the mean of exam 1 or 2, mean of exam 1 was different from that of the mean of exam 2. Now, again, we're testing a population mean, so at some level I'm trying to model this as if the students are some draw from some population of students, which, seems kind of reasonable in this setting, even though it wasn't, they weren't exactly randomly sampled, but it seems like a reasonable thing to try and do. Okay, so let me take the summary for test 1. So in R, I just take summary test 1, and I found that the worst that the students did, which wasn't so bad, was a 76%, and the best people did 100%. And then for test 2, similarly, the worst people did was a 71%, and the best a person did was 100%. Okay, so here's a plot. Scatter plot where I have test 1 on the horizontal axis and test 2 on the vertical axis, and let's see, I've arranged it so the axes are the same, so it's both starting at 70 and ending at 100. And maybe there's some suggestion that test 2 the scores were a little bit higher. It seems like more points are lying above the identity line here than below. The correlation was 0.21, and the standard deviation for test 1 was 6, and the standard deviation for test 2 was 6 also. Oh, and the mean from the previous slide, the mean for test 1 was 87, and the mean for test 2 was 90, sample mean. And then on this next plot, what I'm showing is the difference between test 2 and test 1 versus the average of test 2 and test 1. And this plot is basically the previous plot tilted 45 degrees, sort of like kind of turning your head like that. And the reason for doing that, this is called a mean difference plot, right? The difference on the vertical axis and the mean on the horizontal axis. And there's a very famous paper. So Tukey was the person who came up with the mean difference plot. But there's also a very famous paper on sort of retest reliability by Bland and Altman, where they promote mean difference plots and actually show how to do some inference associated with them, so that these plots are quite well known. And one of the reasons for doing them, it's maybe not so necessary for this data set, but if the correlation is high, then you wind up with a lot of blank space if you do the scatter plot in the upper left-hand corner and the lower right-hand corner, and rotating it in this direction actually gets rid of a lot of that blank space and makes for a far more efficient plot. So at any rate, that's a well-known technique, and whenever you're looking at paired observation, I think for many people, looking at the mean difference plot is more natural and almost a starting point when looking at this kind of data. Okay, so now let's actually perform our test. I'm gonna show our code here. I'm hoping that everyone in the class at this point could actually do the test. So the difference, I'm going to do the paired differences. That's test 2 minus test 1. That's this first line. N is just the number of subjects. And I put a comment here that worked out to be 49 subjects. The mean, in this case, worked out to be 2.88. The standard deviation worked out to be 7.61. This is, again, the standard deviation of the differences. Okay, so my test statistic is the square root of the sample size, because remember that's in the denominator, so we could just bring it up to the numerator, times the average difference. Our null value that we're testing against is 0, so I'm just going to leave that out, divided by the standard deviation of the difference, and I have a little comment here that works out to be 2.65. The two sample p-value works out to be 0.01, so we reject. We knew we were going to reject because 2.65 is a big value of a standard normal, and by the time we get to 48 degrees of freedom, we're pretty close to a standard normal. So we knew that 2.65 we were going to reject, and the exact way we calculate this p-value is we take twice the probability of getting a test statistic as large or larger than 2.65 for a t-distribution with n minus 1 degrees of freedom. I think whether you do this with pt or p-norm, you're going to get about the same answer. And then because we're doing a two-sided test, we multiply it times 2 here, so 2 times this t probability. And that gives us our p-value. It works out to be around 0.01. So we reject the null hypothesis and conclude that there does appear to be some difference in the means between test 1 and test 2. I would say you typically don't go through all these calculations. You calculate your differences, and then you just use a function to do the work for you. In this case, the function is t.test in R, but every statistical package has something to do paired t-test. Okay, so we're not going to spend too much more time on paired differences. I'm hoping for everyone in this class that this discussion is no great stretch for them. But let me raise some points. One thing that when you're doing t-test, paired t-test, it's generally worthwhile to ask the question: are ratios more relevant than pairwise differences? And if ratios are more relevant, then consider doing the paired t-test on the log observations rather than the observations themselves. So another thing is, when considering matched pairs data, you always want to do some plots first. Plot the first observation by the second, and then I showed you this mean difference plot, a more efficient plot of the average versus the difference. And again, if you're interested in relative quantities, then do everything on the log scale. What I mean by that is take the natural log of every observation and then proceed with the analysis with the log data, treating it like you would treat the data normally. So anyway, this plot is called the mean difference plot. It was invented by Tukey and is often called a Bland-Altman plot, from the very well-known paper by Bland and Altman, who added quite a bit of inference on top of it. Okay, so as a bit of an aside, since we're talking about paired data, I thought maybe I'd talk for a minute about regression to the mean, because it's a sort of historically famous topic, and it involves one of the sort of eminent characters in the discipline of statistics. That person's name is Francis Galton. And Francis Galton is the cousin of Charles Darwin, and he invented quite a few topics in statistics. And he was the first to recognize that this phenomenon that when you have matched data, high initial observations tended to be associated with lower second observations, and low initial observations tend to be associated with higher second observations. So the example that he gave was sons of very tall fathers tended to be a little bit shorter, still tall, but tended to be shorter. And paradoxically, not paradoxically, but seemingly paradoxically, fathers of very tall sons tended to be a little bit shorter. And as an example from what we were talking about today, second exams for those who scored very high on a first exam tended to be a little bit lower, whereas first exams for those who scored very high on a second exam tended to be a little bit lower. So let's talk a little bit about why this phenomenon occurs. Okay, so the reason this occurs is, imagine if the tests were completely random. Then and the students were IID draws from that distribution. The probability, so the highest observations on test 1 were just random observations. So the probability of a second observation being that high is quite low. It's more likely to be in the center of the distribution. Conversely, a very low test, something that had a very low probability of occurring, given that it's already low, the probability of a second test being that low is small. And so if it's perfect, or if it's exactly noise, if the pairs of observations are exactly noise, then you'll get a lot of regression to the mean. Let's consider the other extreme. Let's imagine if the test was a perfect adjudicator of students' abilities, then and it was perfectly calibrated instrument, and there was no noise, then a student should ideally get exactly the same score on both exams, at which point there would be no variation around an identity line on this plot here that says test 1 by test 2. Okay, now those are the two extremes. One is complete variation and no trend, and the other is 100% correlation, basically all trend, where the test was a perfect instrument. And of course, every practical case lies somewhere, usually somewhere in between. So here's as an example of the 8 people who got below 80 on a test. All but one did better on test 2, and of the 5 people who got above a 95 on test 1, 3 did worse on the second test. So it's not a tremendous amount of regression to the mean, but some certainly is there. And here I draw the identity line. Okay, so let's discuss this phenomenon a little bit more, and we're going to assume that the data has been normalized. So what does that mean? That means we want the data to have mean 0, variance 1. So in this case, the mean of the first test was 87, the mean of the second test was about 90, and the standard deviation of the first test and the second test were both about 6. So for every first exam, we will have taken the exam, subtracted off 87 and divided by 6, and then for every test, second test, we would have subtracted 90 and divided by 6. So, and of course we would have done it with the exact numbers, not just the rounded numbers like I'm suggesting. And then in that case, we'd have the empirical mean for test 1 would be 0, and the empirical standard deviation for test 1 would be 1, and the empirical mean for test 2 would be 0, and the empirical standard deviation for test 2 would be 1. So that gets rid of any sort of shift effects or scale effects. Now, when we're talking about testing about the paired data, we were exactly looking at shifts in the mean. So here we've gotten rid of the mean information by recentering the data at 0. So if there's no regression to the mean, the data would just scatter about an identity line. Well, if there was exactly no regression to the mean, it would fall perfectly on an identity line. But the more scatter there is about the line, the more regression to the mean there is. So the best fitting line goes through it actually goes through the average, and since we normalized our data, it goes through the point 0, 0. And it has slope. I wrote it out here, the correlation between test 1 and test 2 times the ratio of the standard deviation of test 2 to the standard deviation of test 1, which we normalized the standard test 2 and test 1, so these standard deviations are exactly 1. So the best fitting line goes to the has slope correlation test 1 by test 2. Okay. Okay, so just rehashing something from the previous slide. The best fitting regression line has slope correlation test 1 time correlation of test 1 and test 2, which in general is going to be less than 1. In a case where it's 1, there isn't much statistics left to do. So this will shrink. This will be shrunk towards a horizontal line, telling us our expected normalized score for test 2 will be this correlation times the normalized test 1 score. So if the correlation is 0.95, then your estimated test 2 score will be 0.95 times your estimated test 1 score. And this line sort of appropriately adjusts for a regression to the mean for test 2, conditioning on test 1, or equivalently, test 1 conditioning on test 2. If we knew your test 2 score and we wanted to guess what your test 1 score was, normalized test 2 score is, and we wanted to guess what your normalized test 1 score is, we would multiply by the same correlation. On our plot, the slope of the line will be test 2, will have this slope correlation test 1, test 2, where here I'm assuming test 2 is the vertical axis and test 1 is the horizontal axis. If we wanted the slope going in the other direction, the slope would obviously be the inverse. Well, I don't know how obvious that is, but the slope will be the inverse. So just to rehash, in either case, if you want to adjust for regression to the mean, you're multiplying the test, the normalized test that you have, and the one that you'd want to predict, you would multiply it by that correlation. But let me just show you a plot here. This will probably make it a little bit easier. So here I have normalized test 1 score on the horizontal axis and normalized test 2 score on the vertical axis, and the slope of this line here is the correlation between the two, which is about 0.21, and that's the regression line of test 1 on test 2. I show an identity line here in the middle, and then if you wanted to do the same thing, as if you had test 1 on the vertical axis, then you would use this almost vertical-ish looking line here, and that's just the inverse. That has slope inverse of this correlation here. Notice both these lines pass through the point 0, 0. Okay, and this phenomenon, and so this line, notice how it's you know, when now we're looking at test 2 and we want to predict our test 2 score from our test 1, it's very flat, right? It's very flat, suggesting that there wasn't a lot of correlation between the two tests, and that amount of noise means that there's a fair amount of regression to the mean, and so that if we want to predict our test 2 score from our test 1 score, we're shrinking it quite a bit. And then you can see the same thing in the other direction, that it becomes the adjustment for the regression to the mean becomes very vertical, and that's because the correlation was quite low because there was quite a bit of noise. Notice as the points, if they were to fall more and more on an identity line, so they would kind of collapse around this identity line, then these two cross-haired lines would sort of go like this, and they would converge to the identity line themselves, and that would mean that there was very little regression to the mean. Anyway, it's a neat historical story that Francis Galton figured this out, and his discovery of this was something that led to the discovery of the far more advanced topic of regression. But let's just make some final comments about this. So an ideal examiner, I guess I'm not an ideal examiner from this test I gave. There would be little difference between the identity line and the fitted regression line. And the more unrelated the two exam scores are, the more pronounced the regression to the mean. So, and this is something I heard a talk about this once, that there was a question of how much of our discussion of sports is really discussion of regression to the mean. So the idea is that there's a lot of noise in, say, teams or players' performances, and the ones that do the best in any one given year is a combination of them just being better plus random variation. If that random variation is very high, then there's a good chance that the following year, or the following season, or whatever, they'll have a far lower performance in whatever statistic or measure you're talking about. So, for example, in in baseball, a popular sport in the U.S., if someone has a particularly high batting average early on in the season, there's a good chance they'll regress to the mean in the latter half of the season. And the reason for that is because there's a component of it that is performance, that's inherent, that's the player's skill, and then there's a component that's random variation. And the larger the amount of random variation, the more you'll see regression to the mean. And in that case, the discussion is a lot of discussion about sports, I think, actually amounts to discussing regression to the mean, that sometimes the players that have huge rebounds were just unlucky, and the players that initially and then got luckier in their when they were having their rebound, and the players that did extremely well and then did a lot worse, their intrinsic ability may not have had changed too much, but simply they were lucky early on and then less lucky later on. Okay, so let's get back to some far more pedestrian points now. Anyway, regression to the mean is a very fun topic, and I would suggest you read up on it. I also read up on Galton. He was quite an interesting character. His name is Francis Galton, and he was just a remarkable figure in history. And so I suggest you read up on Galton just out of interest. Anyway, so let's get back to some of the more straightforward things we're going to talk about. The extension not to paired data but to independent groups shouldn't really come as a big surprise either. I'm hoping at this point in the class, after having taken Boot Camp 1, that a lot of this discussion will just come very naturally to you. So let's suppose we want to test H0 mu1 equal mu2, where we have two independent groups versus that they are different, or one of the two alternatives. Then, assuming a common error variance between the two groups, we would have this statistic right here. Okay, our natural estimator of mu1 minus mu2 would be, let's say x bar is group 1 and y's are for group 2, then our natural estimator of mu1 minus mu2 would be x bar minus y bar. Under the null hypothesis, that would have a hypothesized mean of 0, so we don't need to subtract anything off up here on the right. And then the standard error of x bar minus y bar is the common standard deviation across each group times square root 1 over the sample size in the first group plus 1 over the sample size in the second group. And I hope everyone's capable of deriving that. And this follows a t nx plus ny minus 2 distribution under the null hypothesis and the usual assumptions. And we covered this in Boot Camp 1 when we talked about confidence intervals. Basically, when we created the interval x bar minus y bar plus or minus this t quantile times this standard error. So it's exactly the same thing, and it follows exactly the same logic. Here it's, the normalized test statistic is estimator minus hypothesized value under the null hypothesis divided by standard error. It follows the same logic as we've been doing for one sample test, so it should be no great stretch for anyone. Then if you have large sample sizes, it shouldn't be surprising for you that the statistic on the previous page follows a normal distribution. If you're not willing to believe that the variance is the same in the two groups, then the standard error of x bar minus y bar works out to be square root sx squared, where sx squared is the variance in group 1 divided by nx, plus sy squared, which is the variance in the second group, divided by ny, which is the sample size in the second group, square root of the whole thing. And so, of course, if the variance were the same, then you would be able to pull it out, and you get the formula from the earlier part. So just to remind you, I don't think I mentioned it on the previous slide, that the S sub p from the previous slide is the pooled variance, whereas here now we're talking about the variance within group 1 sx squared and the variance within group 2. So anyway, this follows a standard normal distribution if nx and my are large, and it approximately follows a student's t-distribution if the x and y's are normally distributed and independent both within and between groups. But there's this crazy formula for the degrees of freedom, and the approximate degrees of freedom are Sx, this formula here, I'm not going to read it out loud. And you can plug into it if you want. And it turns out to be fairly accurate. The distributional approximation turns out to be fairly accurate. And so you can do this. It's a little bit of a crazy formula, and there isn't, as far as I know, a ton of obvious intuition as to why it works out this way. But what you want to think about it is that it's not surprising that x bar minus y bar divided by its standard error follows something, if the data are normal, that it follows a distribution that looks like a t-distribution. And the fact that it doesn't follow exactly a t-distribution falls out from the fact that we don't have the common variance. But it seems reasonable that you would be able to pick the degrees of freedom that approximate the actual distribution of this normalized statistic to be as close as the one we're using with these approximate degrees of freedom. And note the degrees of freedom can be fractional, so it's okay that this doesn't work out to be an integer. And then a couple of notes. So our connection between hypothesis testing and confidence intervals still holds. If your independent group T interval it contains 0, then you will fail to reject the independent group t-test for equality of means, provided you calculated the standard error in the same way, and vice versa. If you construct a confidence interval by finding all the hypothesized values for differences of means for which you fail to reject, you would wind up exactly with the appropriate t confidence interval. Another thing that comes up all the time, which is people want to test for equality of means by constructing a confidence interval for group 1 and a confidence interval for group 2, and then seeing if those confidence intervals overlap. And that procedure works in one sense, that if the confidence intervals don't overlap and you reject, that's an accurate statement. But if the confidence intervals can overlap, and this test statistic, the test statistic constructed correctly would reject, but the confidence intervals do overlap. So the fancier way of saying is that this procedure of checking whether independently constructed intervals overlap just has lower power than just doing the right test. Also, it has a potential really bad abuse that I've seen happen, is that people construct an interval for group 1 and an interval for group 2, but they fail to acknowledge that people are paired. And then they do this procedure. And then that's quite bad, because then you're throwing out an incredible amount of information in the pairing. right? And or the purpose of the pairing. Sometimes the purpose of the pairing is to account for confounders or something like that. So you're both either throwing out information or eliminating the entire reason for that the pairing occurred. So don't do that. But I know no one in this class would do that anyway. Okay, let's go through an example. Suppose instead of having repeated data on 2 exams, that we randomized to 2 teaching modules and each group took the same exam. So I'm going to treat the data from before as if it was independent group data, just to illustrate performing the calculations. It wasn't actually what happened, but whatever. So imagine it, but here's a setting where we would analyze the data this way rather than treating it as paired. So, and the easiest way to recognize that you don't have paired data is if your n's are different. But that could also be misleading because you could have some missing data and have different n's. So at any rate, the easiest way to determine whether your data is paired is ask yourself this question: are my data paired or not? And then you'll know. Okay, so here we have 2 modules that we randomized students to, 50 students in each. The mean for one was about 87, the mean for the other was about 90. We've thought it through and realized that no, there was no pairwise association. Student 1 from group 1 has nothing to do with student 1 from group 2, and so on. The standard deviations were both about 6. So here, the pooled standard deviation, because the n's are the same, works out to be the average 6.065 of the variances. Remember, the pooled standard deviation works out to be the average of the variances, not the average of the standard deviations. So that does work out to be 6.065. And then our test statistic is the difference in the means, 89.8 minus 86.9, divided by the pooled standard deviation estimate, which go back to boot camp 1 and look at how we do the pooled variance estimate. But when the sample sizes are equal, it works out to be the average of the variances. So in this case, it would be square 6.07 and average it with the square of 6.06, then square root. You wind up with 6.065 times square root 1 over 50 plus 1 over 50. And that's your test statistic, and you do the rest. You check whether this test statistic is big enough to reject. And the sample sizes are big enough to where you can just compare this to a z distribution. The difference between a z and a t is irrelevant for sample size this large. So we're moving through this stuff kind of quickly because we want to get to some more interesting stuff, and I feel like we've mostly already covered this stuff by covering independent and paired group confidence intervals. But just some final notes. Look over the review notes on formal test for equality of variances between two groups. I'm not a huge fan of this. Some books tell you to employ the following strategy: evaluate whether or not the variances are equal by performing a test of equality of variances, and then if you reject, do the unequal variance test, and if you fail to reject, do the equal variance. I never liked those kind of recipe approach to statistics. I would say, well, first of all, these tests aren't very good. They rely on the F distribution. They're heavily dependent on the normality assumption. So I would say just do a bootstrap. If you want to test equality of variances, do some sort of bootstrapping, resampling type thing. Don't do this F test. We have better things now, so just do them. And then for smaller sample sizes, just rely on exploratory data analysis. But in general, if you're concerned about equality of variances, just use the unequal one, and that solves the problem right there. Okay, and then some very final comments. I know I keep saying final comments, and then lying. Suppose you have equal numbers of observations for 2 groups, and let's label the groups X and Y, and the data. The data is random variables X and the random variables Y. If the data are matched or paired, then the standard error of the difference is estimating sigma squared Y plus sigma squared X, both over n, minus twice the covariance divided by n. And you can do this calculation if you'd like, or you can just trust me. square root of the whole thing if you want to standard error. If you ignore the matching, then the standard error of the difference is estimating this square root. My point is, in many cases, by ignoring this correlation, you're unnecessarily inflating your standard error, right? If this covariance is positive, right, then this -2 covariance over n, you're throwing out a positive term, and this is the idea that, for example, if you're comparing exams and you want to know whether exam 1 was harder than exam 2. If you threw out the information that it was the same students taking it twice, then you discard the fact that some students study more than others, some students maybe have different backgrounds than others, and so on, and so some students will consistently do well on exams, and some students will consistently do poorly on exams, and that is encoded in this -2 covariance term, and that's saying that variation associated with inter-student variability, that you're throwing that away and absorbing it into the rest of the variance. So at any rate, the point is that if you treat group data as, or you treat paired data as if it's grouped, you are missing out on some. You're missing out on an important term in the covariance, and we can actually characterize what that term looks like. Now, you might think to yourself, why in the world would anyone ever run a non-paired experiment then? And I think, for more complicated settings, the rule isn't always the case that the pairing always yields lower standard error. So in more complex settings, other things can happen. As an example, if you're studying test, there might be there might be a learning effect, right? That you don't want to intrinsically study. Students may, on the second exam, might simply be better by virtue of having already taken the first exam. So it's not fair to say, is the second exam better? It's harder than the first exam, or easier than the first exam, when the students have had an exam to practice and get used to the teacher's style. That sort of learning effect is an obvious thing. So if you really wanted to investigate the intrinsic properties of exam 1 versus exam 2, you might want to study an independent group exam, because otherwise with only data where exam 2 has been tested after exam 1, you can never learn about that learning effect, right? For all the data points, exam 2 was after exam 1, so you can't investigate that. Now, so there are study designs where they try to both take advantage of the pairing and investigate these sorts of learning effects. And I think you're probably thinking to yourself what the obvious thing that you would have to do. Well, for some people, they would have to take exam 2 first, and other people, they would have to take exam 1 first. And maybe in the setting of an exam, this isn't a reasonable thing to do. But in the setting of drug development, it is a reasonable thing to do. Let's suppose not 2 exams, but you're testing 2 headache medications. Then you might, for every patient, give them headache medication 1, have a washout period, then give them headache medication 2. And then for another set of patients, give them headache medication 2 first, and then give them headache medication 1 second. And those kinds of designs are called crossover designs, and they've randomized the order in which the people receive the treatment in order to adjust exactly for this learning or carryover, or whatever you'd like to call it, effect. But anyway, my larger point being that the point of this slide is not to say pairing is always better than independent groups, but simply to say that if your data are paired, treating them as if they're independent is both wrong from the point of view of assumptions, but also in some cases can actually hurt you in terms of actually making you less likely, inflating your standard error. Oops, I guess that means I gotta go.